Okay, well, you should have got back your graded first assignment. The average for the first assignment is a little more than 25 out of 30, works out to a little more than 83%, so that's fairly good. You should receive a solution set by email sometime today, and what you ought to do is compare your solutions with the solutions in the solution set. That'll give you an idea as to what had been expected relative to what answers you gave. Of course, there isn't going to be a whole lot of difference because the average score is pretty high, so I don't think too many of you are going to find a lot of difference between what you turned in and what you get. But after you see these solutions, you may feel that your assignment was perhaps not graded as you might have hoped. Okay, so if you have a problem with the grading, I'd say first take a look at the solution set so you know what was expected, then take a look at the answer you gave, and then what you want to do is you want to go and talk to the TAs first, and most likely they will resolve the problem at that point. But if you're still unhappy, you want to come and talk to me about the grading. Okay, now our first exam is set for the next lecture. As I said, the syllabus is posted on the web, and hopefully you're fairly well prepared for that exam already. Okay. All right, do you have any questions you want to ask?
Is the open book?
Is the exam open book? No, it's not open book. Yeah. Other questions? Yes. Can you prepare a cheat sheet? No, you can't. Okay, it's a closed book exam, and basically you need to be familiar with the different data structures, know how to insert and remove things. If you take a look at the sample exams from the past, you get a pretty good idea of what's expected. Okay. Yeah. Probably the hardest thing about taking this exam is keeping all the data structures straight, because we've seen so many of them for so little time that you tend to confuse one structure with the other. Okay. All right, other questions? Will you be needing calculators? No. Yeah. Okay. Okay, so in the last lecture we took a look at Fibonacci heaps. These were an extension of binomial heaps. We basically saw how the different operations are performed. And today what we want to do is we want to take a look at the complexity analysis, in particular the amortized complexity. Okay. So what I'd indicated was that the actual complexity for the insert is order 1. You just create a new tree and stick it into your collection of trees. The actual complexity of remove min is order of n because the pairwise combines. You could be combining up to order of n trees. Okay. The meld has an actual complexity of order 1. The remove operation, we saw last time that the remove operation had an actual complexity of log n exclusive of the time spent in the cascading cut. Okay. Now, since the height of the trees that are created here could be order of n, okay, something I asked you to go home and verify that if you perform cascading cuts and everything else the way we described, you can end up with trees whose height is order of n. Okay. As a result, the cost of the cascading cut is order of n. Okay. Because you may be cutting off some node near the bottom of this height n tree, and everybody else already has a child cut field set to true, so everybody has to be cut. So the actual complexity of the cascading cut is order of n, and that's why the remove, even though what we looked at last time was log n exclusive of cascading cut, it becomes order of n once you bring in the cascading cut. Okay. The decrease key, the analysis we saw in the last lecture, said it was order of 1 exclusive of the cascading cut. But then the cascading cut is order of n, so once you factor that in, the actual complexity becomes order of n. All right, what we want to show today is that even though the actual complexities are rather bad on 3 of these 5 operations, you can perform amortized analyses and establish that the amortized complexity is log n for 2 of those 3 and is order 1 for the other one. Okay. So really that's what we're going to do today, establish this right column of amortized complexities. Now, to establish the amortized complexities, we need to first establish a bound on max degree. Okay. So recall that the cost of a remove min operation is related to max degree. It's max degree plus the total number of trees involved in the pairwise combine. Okay. Also, when you do a arbitrary remove, you pull out a tree, you take the root of that tree and you throw it out, and then all of its children get added in as top level trees, and you have to reset all of their parent pointers to null. So that takes an amount of time which is linear in the degree of that tree. Okay. So we need to establish a bound on degree, show that the degree of these trees is at most log of n. Okay. So that's the first thing we do, and after that we will guess amortized costs using the accounting method and show that those guessed amortized costs are sufficient to pay for everything that takes place. Okay. In other words, show that the potential is always non-negative. Okay. All right, so first let's tackle the max degree problem. Okay. All right, so to establish the max degree, what we're going to do is we're going to show that the number of nodes in a tree that's created here with a particular degree, the number of nodes will always be at least exponential in the degree. And so from that you'll conclude that the degree is logarithmic in the number of nodes. Okay. Right, so we let n sub I represent the smallest number of nodes in any of the trees that we create. And this would apply also if you were to just pull out a subtree of one of these trees and apply to that subtree, this would still be a bound on the minimum number of nodes in that subtree. Okay. So we're going to derive a recurrence for n sub I. Okay, so we'll describe n sub I in terms of n sub i's with smaller subscripts. So we might come up with an equation for n sub 4 in terms of n0, n1, n2, and n3. And then we'll solve this recurrence. Okay. And actually what we'll do is we'll show that this recurrence relates to the recurrence for Fibonacci numbers, and hence the name Fibonacci heaps. Okay. All right, so we know that n sub 0, okay, if you look at a tree whose degree is 0, so it has no children, you've got to have at least the root in there. So the minimum number of nodes in a tree whose degree is 0 is 1. If the tree degree is 1, okay, so the root has at least one child, then you've got to have at least 2 nodes. Okay, you may have more, but you've got to have at least 2. Okay. All right, this node here might have a child. Okay, in fact, this node here might have 6 children for all you know. Okay. All right, for I bigger than 1, okay, this is where we'll write down a recurrence. We'll relate this to n's for smaller values of I. Okay. Right, so suppose this is the tree okay, which has the smallest number of nodes. Okay, and its degree is I, meaning that the root has I children. Okay, so let this be the tree that has the smallest number of nodes, and its root has a degree of I. Then if you count up the number of nodes in this tree, that will be equal to n sub I. Right, to count up the number of nodes in this tree, we're going to place bounds on the number of nodes in here, the number of nodes there, and the number of nodes there in terms of the n's. Okay, and then we add up all of those bounds to get a bound on n sub I. Okay. All right, so to come up with these bounds, we'll assume that these children, C1, C2, and so on, there are I of them because the degree is I. We'll assume that these have been numbered in the order in which they became children of B. Okay. Again, if you think to the whole collection of algorithms associated with Fibonacci heaps, there's only one algorithm which makes one node a child of another, and that's the remove min during the pairwise combined phase. Okay? So that's the only place people become children of others, and we kind of look at when did one become a child relative to the other. Okay? So from our numbering, we know that C1 became a child of B before C2. Okay? And C2 became a child of B before C3, C3 before C4, and Ci from this collection was the last one to become a child of B. Okay. All right, so from the numbering that we have, we can draw this conclusion, which says that when, for example, C2 became a child of B, okay, so when C2 became a child of B, the degree of B was at least 1 because C1 was already there. Okay. When C3 became a child of B, the degree of B was at least 2 because C1 and C2 were already there. B may have had other children that have been cut off because of the child cut or because of cascading cuts. Okay. But at a minimum, we know that when C3 became a child of B, C1 and C2 were there. So at that time, the degree of B was at least 2. Okay. Similarly, when C sub I became a child of B, the degree of B was at least I minus 1 because C1 through Ci minus 1 were already there. Okay. All right, so that's the first observation we make. Okay. So from this observation, we can derive a bound on the degree of each of these subtrees at the time they became a child or a subtree of B. And to get that bound, we know that since the only place one fellow becomes a subtree of another is during pairwise combine, and pairwise combine combines two trees of the same degree. Okay. So we know that at the time C2 became a subtree of B, the degree of C2 was exactly equal to the then degree of B. Similarly, when C6 became a child of B, the then degree of C6 was exactly equal to the then degree of B. Okay? So we know that the degree of CK at the time when CK became a child of B was exactly equal to the degree of B at the time that CK became a child of B, because that's the rule for pairwise combine. And from here, we know that degree of B at that time was at least k minus 1, okay, from this line here. Right. So I plug that in. Okay. Okay. So the conclusion I draw is that when CK became a child of B, its degree was at least k minus 1. Okay. It might have been higher, but it's at least k minus 1 at that time. Okay. All right. Any questions with that conclusion? All right, so if that was the degree when CK became a child of B, what can you say about CK's present degree? By how much can a node's degree drop after you become a child of someone else? Yeah, the most you can drop is 1. Okay, so now it's got to be k minus 2 at least. Okay, so for example here, if you look at this fellow here, at the time it became the child of B, let's say it had some degree, let's say its degree was 20. Okay, at that time its child cut value gets set to false. If you lose a child, your child cut value gets set to true. So from 20 you drop to 19. If you lose another child, there's a cascading cut, and you become a top level tree. Okay. You're not a top-level tree, so you couldn't have lost more than one child. Okay. So if your degree was at least k minus 1 at the time you became a child of B, you're still a child of B. Your degree now is at least k minus 2. You couldn't have gone down to k minus 3 because then you'd have lost 2 children, and you should have been cut off from your parent. Okay. All right, so from the way our algorithms are structured, we know that the current degree of ck is at least k minus 2. And of course, degree cannot become negative, so a more accurate way is to say it's the larger of 0 and k minus 2. Okay. All right, any questions about this conclusion? Okay. All right, so once you have that, then we can figure out how many nodes each of these trees has in terms of n. Okay. We come up with a lower bound on the number of nodes. Okay. So we know that this tree, for example, C1, okay, has at least its current degree is at least 0. Okay. So you put k equals 1, you get a minus 1, so the degree is at least 0. And so the number of nodes is at least n0. Okay. Because by definition, n0 is the minimum number of nodes in any subtree whose degree is 0. Okay. This fellow's degree at this time is at least 0, maybe more. So it's got to have at least n0 nodes in it. C3's degree right now is at least 1. So it's got to have at least n1 nodes in it. Okay. C4's degree is at least 2. So it's got to have n2 nodes or more. Okay. Ci's degree is at least I minus 2. Okay. And so it's got to have at least ni minus 2 nodes in it. Okay. So from this, we arrive at this thing. The n0 term tells you the minimum number of nodes in C1. And then the next n0 out here covers C2. The n1 covers C3. The n2 covers C4, and then finally the n sub I minus 2 gives you the minimum number here in C sub I. Okay. All right. So the smallest possible number of nodes in this whole tree, you add up the smallest possible number of nodes in each of the subtrees, and then you bring in a 1 for the root node. Okay. All right. Do you agree with that equation? All right, so once you have that equation, we just kind of replace this n0 with a 1. You get this. Okay. And those of you who have seen the Fibonacci number series might see a similarity with this expression and the definition of Fibonacci numbers. Okay. So Fibonacci numbers are defined as a sequence f0, f1, f2, and so on. F0 is 0, F1 is 1, and then the most common recurrence given for F sub I relates it to the two previous ones. But if you do repeated substitution on this, you can rewrite this right-hand side to look as that sum. Okay. So you add up the Fibonacci numbers from 0 to I minus 2, then add another 1, you get the ith number. And if you compare that to the sequence or the recurrence we have for our n's, okay, so n0 is 1 more than f0, n1 is 1 more than f1, and n sub I looks a lot like that, except that we are adding a 2 instead of we're adding a 2 here instead of a 1. Okay. So these two series are very closely related, and in fact, you should be able to show that the ith number here is actually the I plus 2th number in the Fibonacci series. Okay. So these two series are actually the same. This one is just shifted by 2. Okay. All right, so the minimum number of nodes in one of the trees we create, whose degree is I, the minimum number of nodes is the I plus 2th Fibonacci number. And the I plus 2th Fibonacci number is known to be approximately 1 plus root 5 over 2 raised to I. Okay. So the Fibonacci numbers grow exponentially in I. The base of the exponent is not 2. The base of the exponent is 1 plus root 5 over 2. All right, so from this, you can show that the max degree is log of n base phi, where phi is the base of the exponent we had before. Right, so the n sub i's grow exponentially in I, and therefore the degree is bounded by log of the number of elements in the tree. Okay. And precisely it's given by this expression here. Okay. All right, so we don't get binomial trees anymore. We get some odd-shaped trees, and for these odd-shaped trees, we can show that the minimum number of nodes is n sub I being the degree of the root, and in turn, that tells us that the max degree is logarithmic in the number of nodes in the tree. Okay. All right, any questions about this step in the derivation? Okay. All right. So now we're going to use the accounting method. We're not going to use the aggregate method, same reasons as before. We're looking for amortized costs that are different for different operations. So we'd either use the aggregate or the accounting, or we'd use the potential function method. Okay. All right, so let's try the accounting method first, and then later I'll just put down the potential function that you can use, and then you can go home and use that potential function and derive the amortized costs for the different operations. All right, so in the accounting method, we need to guess the amortized costs, and then we need to show that the potential is non-negative. The potential simply keeps track of the total amount of overcharge. Okay, you charge operations their amortized cost, so you add up the amortized cost of the operation so far, and you should always have an overcharge. You should not have an undercharge. Okay. All right, so for the insert operation, we're going to guess that it has a cost of 2, which is really the same amortized cost we guessed for the case of binomial heaps. Okay. Well, once you guess the cost, the other thing you need to do is you need to show how you're going to use this guessed cost. Some of it will get used to pay for the current operation, or at least part of the current operation, and the balance will get saved as a credit. And then you need to have an accounting scheme to keep track of the credits. Okay. And then showing that the potential is non-negative essentially amounts to showing that you never have negative credits. Okay. All right, so we're going to use one of these 2 units that you're charging the operation to pay the actual cost of the operation. The actual cost of an insert is 1. So that's going to leave us with 1 unit of overcharge, and our accounting scheme is going to keep that 1 unit of overcharge as a credit on the tree that you create. Okay. The credit scheme we're going to use is going to ensure that every top-level tree, okay, has a credit. That credit will eventually be used when you do a pairwise combine, just like it was in the case of a binomial heap. Our accounting scheme will also ensure that every node that has a child cut value of true has a credit of 2. And that credit is going to be used for the time you cut this node away from its parent in a cascading cut. So when you cut a node away from its parent, that's going to cost you 1 unit to just remove it from the parent and insert it as a top-level tree. Okay. So since the node whose child cut is true has a credit of 2, one of those 2 units of credit will be used to pay for cutting it away from its parent. That still leaves you with 1 credit, which you can leave on this tree because it now becomes a top-level tree, and every top-level tree must have a credit of 1. Okay. So our accounting scheme, the credits will be kept on top-level trees. Every top-level tree has a credit of 1. Every node whose child cut field is true will have a credit of 2, and that's going to be sufficient to pay for everything we might do. Okay. All right, so just keep that in mind as we keep track of credits. Okay. All right, so here you create a new tree, we have to leave it with a credit of 1, and fortunately our guess cost is 2, we have an excess of 1, we place a credit of 1 on that newly created tree. Okay. If you look at a meld operation, well, here we're going to guess that the cost is 1. the actual cost is 1, so all of that amortized cost gets used to pay for the actual cost. There are no excess charges, there are no extra credits left. You don't have to place them anywhere. There's nothing left to place. Okay. And we still maintain our invariant. Every top level tree has a credit of 1. Every node with a child cut equal to true has a credit of 2. If it was true before the meld, it's going to be true after the meld. You don't create new trees. You don't change anybody's child cut from false to true. Okay. All right, you look at the remove an arbitrary element, okay, a non-min element. Okay. So, for example, here somebody said remove this fellow. Okay. So to remove this fellow, the operations, if you recall, are you need to pull this tree out of its doubly linked circular list of siblings. Okay. Once you pull it out, then let's pull it out. Okay. All right, so once you pull it out, you need to take the root. Okay, this had a root which was 4. You throw the root away, and then its children get inserted into the top level collection of trees, top level doubly linked circular list. Okay. And you need to change all of these parent pointers to null. This fellow here, its child pointer might have gone to that node, in which case you have to update the child pointer. Okay. So those were the things that we had to do. Okay. And now we have to figure out how we pay for all of that with whatever amortized complexity we guess and whatever credits we may have. Okay. All right, so we're going to guess that this operation has an amortized complexity that is 2 log n plus 3. Okay. The base of the log n is phi because our max degree is known to be log n base phi. Okay. So we're going to guess that, and assuming everything holds up, that would then give us that order log n complexity we said was true for the arbitrary remove operation. Okay. All right, so from this guess complexity, I'm going to use up log phi n units to pay for the cost of setting the parent pointers here to null. Okay. Since the degree of that node 4 is at most log of n base phi, there are at most log of n base phi of these children whose parent fields have to be set to null. Okay. So from here I take out log n base phi of what you're charging it and use that to pay for changing those fellows to null. Other than that work, I have 2 other pieces of work going on. There's the cascading cut, which could have an actual cost of order n. Okay. And then there is a constant work which is associated with pulling that 4 out of its doubly linked circular list, throwing away the node, taking the doubly linked list of children and combining it with the doubly linked top level list, changing a child pointer in the parent of 4, possibly. Okay. So for that constant work, I use up 1 unit from this 3. So that leaves me with log n plus 2 surplus. Okay. Now, as far as the cascading cut is concerned, I'm going to account for the cascading cut separate. Okay. So later I'm just going to look at how I pay for all my cascading cuts. Okay. So at this time I'm not going to worry about where the cascading cut gets paid for. Okay. From the guessed amortized complexity of 2 log n plus 3, I'm going to use log n plus 1 to pay for everything that's done in the actual cost except for the cascading cut. And later I'll tell you how I pay for the cascading cut. Okay. So now I'm left with a surplus of log n plus 2. And this surplus is going to remain as credits in the system. And to account for these credits, I'm going to place them in strategic places so I can later come back and use them when I need to. Okay. All right, so keeping track of these credits, okay, I'm going to put I'm going to take log n of that log n plus 2. Okay. And I'm going to put 1 on each of these up to log n trees. Okay. Again, my invariant said that all of these trees must have 1 credit. When I put them up here, there was no credit on them. Okay. So I use up log n of my credits up to log n to place 1 unit of credits here, and eventually that's going to get used in pairwise combines during a remove min operation. Okay. If you don't have log n children, the balance of the credits, you just toss them away. We're not going to use them. Okay. Right, so again, all of the top level trees have a 1 unit credit on them. Okay. Now this operation may take a node whose child cut was previously false and change it to true. That will happen in the cascading cut. Okay. So, so that node that was previously false and now has changed to true, well, you need to leave 2 units of credit on that to maintain our invariant, which said that every node whose child cut is true has a credit of 2 on it. Okay. Unfortunately, I still have 2 units of cost left. Okay. So I'm going to take those 2 units and I'm going to place them on the node whose child cut gets changed from false to true, provided there is such a node. In some cases, there may not be such a node, but if there is, you place the 2 there. And the way you're going to use those 2 later is when the node actually gets cut off from its parent, you'll use 1 to pay for it. And when it gets cut off from its parent, it's going to be put in as a top-level tree, and the other one will be used as a credit on the top-level tree. Again, to maintain the invariant that every top-level tree has a 1 unit credit. Okay. Right, so I do have 2, and I'm going to keep these 2 units on the node whose child cut field changes from false to true, provided there is such a node. If there isn't such a node, you throw away these 2 credits. We don't need them. Okay. All right. The decrease key operation. Okay. All right, so somebody points to some node in the system and then tells you to decrease its key. If the value drops below that of the parent, we need to cut it out from its doubly linked circular list of siblings, and this whole subtree gets promoted and becomes a top-level tree. Okay. So in this case, the 4 was reduced to 0. Okay. Right. Now, the actual cost of doing all of this, exclusive of the cascading cut, is order of 1, because you just pull this subtree, you just pull it out of its doubly linked circular list of siblings, which is an order 1 operation. You reduce the value, and then you possibly update the minimum element pointer. Also, if this fellow's child field was previously going here, you have to change its child field. You change this parent field to null. Okay. That's pretty much all you do, and that's all constant amount of work. Okay. So actual cost is order 1, plus the cost of the cascading cut, which, as I said earlier, could be order of n. All right, so to pay for all of that, I'm going to guess an amortized cost of 4. So order 1 amortized cost. Okay. And the way I'm going to use this is 1 unit is going to get used to pay for everything other than that cascading cut. Okay. And everything other than the cascading cut is order 1 work. Okay. So I said I'll worry about the cascading cut later. I'll pay for that later. I'll show you how to pay for it later. Okay. All right, so now I'm left with 3 units of excess charge, which I'm going to keep as credits in the system. Okay. So one of those 3 units is going to get placed on this newly created top-level tree, maintaining the invariant that every top-level tree has a 1 unit credit on it. And that's required when you do pairwise combines. Okay. All right, so I put 1 unit of those 3 there. So now I'm still left with 2. And those 2, again, I know that when you cut this fellow out from here, there may be a cascading cut. Perhaps this is deep in some tree, and this guy's child cut value previously was true. So then you have to cut this fellow off go to its parent, you may have to cut the parent off, and so on. Okay? So as you go along, there may be one last node whose child cut value previously was false and now gets changed to true. Okay? And we better have 2 units of credit to place on it. And the reason we need those 2 is to pay for the things that take place in a child cut, and to leave a credit when that node becomes a top level node. Okay. All right, so again, that's the same thing that we did for the arbitrary remove. Keep 2 units of credit on the node whose child cut value changes from false to true, provided there is such a node. Okay. All right, so hopefully you're kind of convinced, at least so far, we have made sure that every top level tree has a credit of 1. Every node whose child cut value is true has a credit of 2. Okay. All right. Let's look at the remove min operation. Okay. Here we're going to guess 3 log n. It's the same that we guessed for binomial heaps, except there the base was 2. All right, so if you go back to the analysis for binomial heaps, there we came up with an inequality like this, which said the actual cost was 2 log. In that case, it was base 2. Okay. So the only thing that changes is instead of base 2, you now have a base of phi. Okay. And this is the number of trees that you had just before the pairwise, just before the remove min operation. So we'll start from there, because up to there the derivation is the same. And then we'll take our 3 log n, and we're going to allocate it pretty much the same way as we did for the binomial heap case. Okay, this part of the analysis is pretty much the same as that for binomial heaps. Okay. And there, if you recall, this part of it, which, as I said, in the case of binomial heaps was 2 log n base 2 minus 1. That part of it was paid for from the amortized cost. Okay. And that's still going to be the case. Okay. So that's going to leave us with a surplus of log n plus 1 that hasn't been used to pay for anything. Okay. And so that log n plus 1 is going to be used as credits. Okay. And those credits are placed on the trees following the pairwise combine. Since the maximum degree is log n, you may be left with log n plus 1 degree, trees, each tree having a different degree. And so each of those gets 1 unit of credit to maintain the invariant that every top level tree has 1 unit of credit. Okay. So this is what you charge the operation. From that charge, you only use this much, 2 log n minus 1, to pay for it. The balance is used as credits on the newly created top-level trees from the pairwise combine. Okay. And that means you've got this much that you haven't paid for, and you need to come up with a place to pay for it. Okay. And that gets paid for from the credits that you have. Okay. So the way you pay for it is, of course, this is paid for from the amortized cost. Each of these trees, this is the number of trees just before the remove min, the top level. Each of those trees has 1 credit on it. Okay. So you use all of those credits to cumulatively pay this much of the cost. Okay. So we're able to pay for all of the remove min cost. Right, the only thing we haven't paid for is the cascading cut. So a cascading cut could cost you order of n because the height of these trees is order of n. The nice thing about a cascading cut is a cascading cut starts at a node, the node that you cut off. You go to the parent. If the parent's child cut value is false, you just change it to true. And then we leave a credit of 2 from our costing scheme that we just had. But if its child cut value is true, you cut it off. You cut it off, you promote it, it becomes a top level tree. Okay. And that costs you 1 unit of work. And then you go to the grandparent, and if that was true, you cut it off. And that takes you another 1 unit. Then you go to the great grandparent. If its child cut is true, you cut that off. So each node you see whose child cut value is true costs you 1 unit. And each such node also creates one new tree on which you have to leave a credit. Okay. Fortunately, each of the nodes that you cut off has 2 units of credit sitting on it because its child cut value is true. Okay. And one of those 2 units is used to pay to actually cut it off. Okay, you have to pull it out of a doubly linked circular list, change a parent pointer, and so on. And the other 1 unit is left as a credit because the fellow you cut off becomes a top level tree. Okay. All right, so you've got enough credits in the system to pay for your cascading cuts. Okay. All right, so what we've shown is that if you use the guessed amortized costs, you in fact are able to pay for all of the actual costs in any sequence of operations. And so you have a correct guess. Okay. Right, now we will certainly do this same analysis using the potential method. In the potential method, you start by guessing a potential function. You show that the potential function is always non-negative, so you have a correct potential function. And then use this potential function together with your knowledge of actual cost to figure out the amortized cost. Now, normally using the potential function method is a challenge, just like the accounting method, because you have to do some guessing. In the accounting method, you got to guess the amortized costs. In the potential method, you have to guess the potential function. Okay. But once you've done one of these two, using the other method is simple. And of course, in any real situation, if you had success using the accounting method, you would not bother with the potential function method. And if you had success with the potential function method, you would not bother with the other one. Okay. But at least as an academic exercise, if you've done one, you may want to see how things would work out using the other method. Okay. Now, the potential function is supposed to keep track of the credits in the system. Okay. And once you've done the accounting analysis, we already know what the credits are that make the thing work. Okay. And the credits are, every tree in your system must have a credit on it. So you add up all the trees and all of the Fibonacci heaps. Okay. So number of min trees j is the number of min trees for the jth Fibonacci heap. Again, remember, if you're doing melds, you got to have more than one Fibonacci heap around. Okay. So you add up all of the top level trees. That gives you the first sum out here. Okay. And we know that each one of those fellows has 1 credit on it from our previous analysis. Okay. And then you take 2 times the number of nodes whose child cut value is true. Because we know from the previous analysis we were placing 2 credits there. Okay. So this PI here really just adds up all of the credits we were keeping track of in our previous accounting scheme. Okay. And therefore we know that if we use this potential function, we're going to come up with the same amortized cost that we guessed in the previous case. All right, so as I said, in a real application of this method, we would not have done the accounting analysis, and so the challenge will be to guess this. Okay. And then once you've guessed this, deriving the amortized costs that were previously guessed would be fairly simple. And once you have guessed this, basically what you would do is you would note from here that the initial potential is 0. Okay, if you haven't performed any operations, this is the potential after the ith operation. So you haven't performed any operations, the number of min trees is 0, there are no nodes with a child cut of true, so your initial potential is 0. Okay. Also, the number of trees can never become negative, nor can the number of nodes with child cut value true become negative, and therefore the potential function is always non-negative. Okay. And so we know that we have a valid potential function, and therefore if you use this potential function in a manner similar to the way we used it for binomial heaps, whatever amortized cost we get would be correct amortized costs. Okay. Now you can go home and start from here and use the formula for amortized cost equals, I guess, change in potential plus actual cost. Okay. And you should come up with the same figures we had guessed earlier. Okay. All right, any questions? Okay. Again, keep in mind, these analyses are much harder than anything you might get asked on a test. So but you can be sure if you can do this, you can do any test question. Okay. Okay.